Hello there, and welcome to ThinkSleep, where we explore the universe's deepest questions at a pace that lets your mind wander and rest. Tonight, we're going to ask something that feels both profound and unsettling. What if, in all the vastness of space, across all those billions of galaxies and trillions of stars, we are completely, utterly alone? Not alone on Earth, but alone as the only civilization that has ever looked up and wondered. It's a question with no easy answers, so settle in, let your thoughts slow down, and if this kind of exploration speaks to you, I'd appreciate if you'd like this video, subscribe, and leave a comment letting me know where in the world you're listening from tonight. On a clear night, away from city lights, you can see perhaps 2,000 or 3,000 stars with your naked eye, each one a sun, many with their own worlds circling in the darkness. It's beautiful, humbling, the kind of view that makes you feel small in the best possible way. But there's something else about that view, something we don't often talk about. It's silent, profoundly, completely silent. We've been listening for decades now, really listening, with radio telescopes pointed at the sky, scanning frequencies, searching for patterns that couldn't be natural. We've sent our own messages out, mathematical primers, images, sounds of Earth, hoping someone might hear and respond. We've looked for signs of engineering on cosmic scales, structures that would require technology, intelligence, purpose, and we found nothing, not a whisper, not a signal, not a hint that anyone else is out there doing what we're doing, wondering what we're wondering. This silence has a name in scientific circles. They call it the Great Silence, and it's one of the most puzzling observations in all of astronomy. Because when you do the math, when you count the stars and estimate the planets and factor in the age of everything, the universe should be, if not crowded, at least populated. There should be someone out there, many someones. And yet, when we listen, we hear only the background hum of radiation left over from the Big Bang, the natural crackle of cosmic processes, but nothing deliberate, nothing designed, nothing that sounds like hello. You might think this is just because space is big, and you'd be right. Space is unimaginably big. The nearest star to our sun is over 4 light years away, meaning light. The fastest thing we know takes more than 4 years to travel between them. But here's the thing, the universe isn't just big, it's old, nearly 14 billion years old, and if life can emerge, if intelligence can develop, if civilizations can arise, they've had an enormous amount of time to do so. Time enough to spread, to build, to signal, to leave marks that would be visible across vast distances. Consider this. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. Let's be conservative and say 200 billion. Even if only a tiny fraction of those stars have planets in the right zone for liquid water, and even if only a fraction of those planets develop life, and even if only a fraction of those develop intelligent life, you're still left with numbers that should produce many civilizations. Thousands, maybe millions, depending on how generous you are with your estimates. And it's not just our galaxy. There are trillions of galaxies in the observable universe, each with billions of stars. The numbers become almost meaningless at that scale, too large to hold in your mind comfortably. And yet, in all that vastness, in all that time, we seem to be alone. Or at least, we seem to be the only ones calling out, the only ones listening, the only ones wondering why no one answers. This wasn't always a mystery. For most of human history, we assumed we were alone because we assumed Earth was special, perhaps even central. The universe revolved around us, literally in early cosmologies. But as we learned more, as we discovered Earth was just one planet among many, orbiting an average star in an unremarkable region of a typical galaxy, the assumption shifted. If we're not special, if our place in the cosmos is ordinary, then surely others must exist. Life should be common, intelligence should be widespread, the universe should be full of voices, but it's not, or at least we can't hear them. And this absence, this silence, demands an explanation. Several, actually. Scientists have proposed dozens of possible reasons why we might be alone, or why we might only appear to be alone. Some of these reasons are hopeful, suggesting civilizations are out there, but we just haven't found them yet. Others are darker, suggesting something prevents civilizations from lasting long enough to make contact. And a few are strange enough to reshape how we think about existence itself. The silence above isn't just an astronomical puzzle, it's a mirror. When we ask why the universe seems empty, we're also asking what it means to be the ones asking, what it means to be conscious in a cosmos that might not contain any other consciousness, what it means to search for meaning in a place that might offer none, and whether the absence of others makes us more precious or more alone. Tonight we're going to explore this silence, not to solve it, because it may not have a solution, at least not yet, but to sit with it, to understand what we know and what we don't, and to consider what it might mean for us, here, now, if we really are the universe's only witnesses to itself. So let's begin where the question begins, with the numbers that suggest we shouldn't be alone, and the growing realization that perhaps we are. There's an equation that haunts astronomers and dreamers alike. It was written in 1961 by a scientist named Frank Drake. Not because he thought he could solve it, but because he wanted to organize the conversation. He wanted to break down the big question, are we alone, into smaller questions that could actually be studied, tested, measured. The equation looks deceptively simple on paper, just a series of terms multiplied together. But each term represents something profound, and when you work through it, you realize you're not just doing math. You're estimating the probability of companionship in the cosmos. The Drake equation, as it's called, starts with the rate at which stars form in our galaxy. That number we know fairly well. About 7 new stars per year, give or take. Then you multiply by the fraction of those stars that have planets. We didn't know this number when Drake first wrote his equation, but now we do, thanks to telescopes like Kepler that have found thousands of planets around other stars. It turns out most stars have planets. The fraction is high, close to 1. Next, you multiply by the number of planets per star that could support life. Planets in the so-called habitable zone, where it's not too hot and not too cold for liquid water. Again, observation suggests this is common. Many stars have at least one planet in this range. Then comes the harder part. You multiply by the fraction of those planets where life actually emerges. We don't know this number. We only have one example, Earth, and from one example you can't calculate a probability. Life might be inevitable given the right conditions, or it might be a 1 in a trillion accident. We just don't know, but let's be generous. Let's say life emerges on a decent fraction of habitable planets. Now you multiply by the fraction of those life-bearing worlds where intelligence evolves. Again, unknown. On Earth, it took about 4 billion years for intelligence like ours to appear. For most of that time, life was single-celled. Then it was simple, multicellular. Then it was complex but not conscious, at least not in the way we think of consciousness. Intelligence, the kind that builds tools and wonders about the stars, came late, very late. It might be rare even among worlds with life. Still, Let's stay generous. Let's say some fraction of life-bearing worlds eventually produce intelligent species. Now you multiply by the fraction of those intelligent species that develop technology capable of communication across space, radio waves, lasers, whatever. This seems more likely if you've already gotten to intelligence, but it's not guaranteed. A species could be intelligent without being technological. They might live in oceans where fire is impossible, or they might simply not be interested in the stars. And finally, you multiply by the length of time such civilizations release detectable signals into space. This is the most troubling term in the equation, because we don't know how long civilizations last. We've been broadcasting radio signals for about a century. Will we still be broadcasting in another century? In 1,000 years? In 1,000,000? Or will we destroy ourselves, or transcend radio, or simply go silent for reasons we can't yet imagine? When Drake first gathered scientists to discuss this equation, the estimates varied wildly. Some thought the galaxy might contain millions of communicating civilizations. Others thought we might be alone. The uncertainty came from those unknowns, especially the last few terms. How common is life? How often does intelligence arise? How long do civilizations survive? We're still uncertain about these things today, more than 60 years later. But here's what makes the equation so haunting. Even with conservative estimates, even if you assume life is rare and intelligence rarer still, the numbers suggest we shouldn't be alone. The galaxy is so large and so old that even tiny probabilities, multiplied by billions of stars and billions of years, should produce something. Someone. Somewhere. Let's do some rough math. Say 1 in 1,000,000 stars has a planet where intelligent technological life emerges. In our galaxy alone, that's still 200,000 civilizations. Spread them out over the galaxy's history and maybe only a fraction exist at the same time as us. But even then, you'd expect thousands to be alive right now, sending signals, building, exploring. Where are they? Or push the numbers the other way. Say intelligence is incredibly rare. 1 in 1,000,000,000 stars. That's still 200 civilizations in our galaxy. Expand to the entire observable universe, and even the tiniest probabilities explode into certainty. There should be someone out there, many someones, and yet, silence. This is why the silence is so strange. It's not just that we haven't found anyone yet, it's that the math says we should have. The universe has had plenty of time, plenty of stars, plenty of chances, even accounting for the enormous distances between stars, even accepting that we might not be able to detect every kind of signal or every kind of civilization. The absence feels wrong. It feels like something is missing from our understanding, some factor we haven't accounted for, some reason the equation doesn't work the way it seems like it should. Some scientists argue the equation is too optimistic. Maybe life is far rarer than we think. Maybe intelligence almost never happens. Maybe technological civilizations last only a few centuries before collapsing, making them invisible to each other across time. These are possible, but they're also just guesses, attempts to make the math match the observation. We're working backward from the answer, from the silence, trying to figure out which terms in the equation need to be adjusted to explain why we see no one. Others argue we're just not looking hard enough yet or are looking in the right ways. Maybe civilizations communicate with methods we haven't discovered. Maybe they're out there but quiet for reasons of their own. Maybe we're like early humans standing on a beach, cupping our ears and hearing no other voices, not realizing the rest of the world is on the other side of an ocean we can't yet cross. Patience, they say. Keep searching. Keep listening. The universe is vast and we've only just begun to look. Both views might be right in some way, or both might be wrong. The uncomfortable truth is that the Drake equation, for all its elegance, doesn't give us an answer. It gives us a framework for our ignorance, a way of organizing what we don't know. And what we don't know is almost everything. We know stars and planets exist. Beyond that, we're guessing. Educated guessing, but guessing nonetheless. And so the numbers don't add up, not because the math is wrong, but because reality refuses to cooperate. The equation says we should have company, and reality says we're alone, or at least we seem to be. Something in the chain of events that leads from hydrogen clouds to conscious beings asking questions about the universe must be rarer, harder, more fragile than we think. Or something happens to civilizations that stops them from being detectable, from lasting, from spreading. The equation points to a mystery but doesn't solve it. And that mystery leads us to a question asked by a physicist over lunch one day. A question so simple it sounds almost naive, yet so profound it still haunts us. Where, he asked, is everybody? The year was 1950, and Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. Fermi was one of the architects of the atomic age, a brilliant physicist with the talent for cutting through complexity to find the essential question. The conversation that day had wandered as conversations do toward flying saucers and the popular press's fascination with alien visitors. Someone made a joke. Someone else mentioned the vast number of stars. And then Fermi asked, almost casually, "Where is everybody?" It wasn't a joke, though it might have sounded like one. It was a genuine question, and everyone at the table understood immediately what he meant. If the galaxy is old and large, if planets are common and life possible, if intelligence can arise and technology develop, then where are the aliens? Why haven't they visited? Why haven't we seen evidence of their existence? The distances are vast, yes, but civilizations have had billions of years to spread. Even travelling slowly, much slower than light, a single civilization could colonize the entire galaxy in just a few million years. That sounds like a long time to us, but it's nothing on cosmic scales, a rounding error in the age of the universe. So where are they? Why don't we see megastructures around distant stars engineered to capture every photon of energy? Why haven't we intercepted their communications, even by accident? Why hasn't anyone sent probes to our solar system to take a look at this interesting yellow star with its collection of rocky and gas giant worlds? The question hung in the air that day at lunch, and it's been hanging ever since. We call it the Fermi Paradox, though Fermi himself never wrote about it formally. It was just a question asked over sandwiches, but it struck a nerve because it captures a genuine contradiction. The universe seems like it should be full of life, and yet it appears to be empty. The paradox is sharper than it first appears. It's not just about whether intelligent life exists elsewhere. It's about visibility, expansion, time. Even if only one civilization in the galaxy decided to spread to the stars, to send out ships or probes or even just self-replicating machines, those emissaries would eventually reach everywhere. The galaxy would fill up not with life necessarily, but with evidence of someone having been there. And we see no such evidence. Our solar system looks untouched, pristine, as if no one has ever passed through. Some people find this comforting. We're alone, which means we're special, unique, the universe's only children. Others find it unsettling. We're alone, which means something is very wrong with our assumptions, or something terrible happens to civilizations before they can spread. The paradox doesn't tell us which interpretation is correct. It just points out that something doesn't fit. Either intelligent life is far rarer than we think, or it doesn't last long, or it doesn't spread, or we're missing something fundamental about how the universe works. Let's consider the expansion question more carefully. Imagine a civilization reaches the technological ability to send ships to other star systems. Maybe they use generation ships, vessels that travel for centuries with populations living and dying aboard. Maybe they use sleeper ships, with crews in suspended animation. Maybe they send robots, machines that can build copies of themselves when they arrive at a new star. However it's done, once it starts, it's hard to stop. Each new colony can send out its own ships. Each robot can build more robots. The spread becomes exponential. One star system becomes 10, 10 becomes 100, 100 becomes 1,000. Work out the math, and even with slow ships travelling at a small fraction of light speed, taking thousands of years between stars, the wave of expansion reaches every star in the galaxy in just a few million years. Maybe 10 million if you're being very conservative. That's fast, cosmically fast. The galaxy is about 10 billion years old. If anyone started this process even a billion years ago, they'd be everywhere by now, including here. But they're not here, or if they are, they've hidden so perfectly we can't tell. Our moon is geologically dead, a museum of impacts stretching back billions of years. If anyone had visited in that time, they could have left traces, markers, technology. We've studied the moon fairly well and found nothing artificial. No monoliths, no buried beacons, no signs of mining or construction. Just rocks, ancient and untouched. The same goes for Mars, the asteroids, the outer moons. Everything we've examined looks natural, shaped only by physics and chemistry, not by intent. So what's the answer? Fermi himself didn't propose one. He just asked the question. But others have spent decades trying to resolve the paradox, offering solutions that range from the mundane to the extraordinary. Maybe space travel is harder than we think. Maybe the distances are just too vast. The energy requirements too high, the dangers too great. Maybe civilizations arise and then stay home, content to explore inward rather than outward, or unable to overcome the gravitational and economic barriers to interstellar expansion. Maybe intelligent life is rare in a way the Drake equation doesn't capture. Maybe the path from chemistry to biology is easy, but the path from biology to intelligence is incredibly hard, requiring not just time but specific sequences of events that almost never happen. Maybe Earth lucked into it, and most planets with life never get beyond bacteria or simple animals. Or maybe intelligence happens but technology doesn't. Maybe most intelligent species don't develop science, don't discover fire, don't build tools that let them reshape their world. Or maybe civilizations don't last. This is the darker interpretation. Maybe there's something about reaching a certain level of technology that leads to self-destruction. Nuclear weapons, climate change, artificial intelligence, bioengineered plagues. Maybe every civilization faces a gauntlet of existential risks, and most don't make it through. They destroy themselves or collapse back to pre-technological states before they ever get the chance to spread to the stars. If that's true, then the galaxy might be littered with the ruins of short-lived species, each one rising and falling in the blink of cosmic time, none overlapping, none surviving long enough to meet any of the others. There are stranger possibilities too. Maybe advanced civilizations transcend physical form, uploading themselves into simulations or evolving into beings of pure energy or mathematics. Maybe they lose interest in the material universe and turn inward, exploring virtual realities far richer than anything planets can offer. Maybe they're out there but incomprehensible to us, operating on scales or in dimensions we can't perceive, as far beyond our understanding as we are beyond ants. Or maybe they're quiet on purpose. Maybe there's a reason to stay silent, to avoid broadcasting your presence. Maybe the universe is more dangerous than it looks, and civilizations that shout into the void don't survive long. This is sometimes called the dark forest hypothesis. The idea that the cosmos is full of hunters, silent and hidden, and making noise gets you noticed by something you don't want to meet. It's a chilling thought, and not one most scientists give much weight to, but it's hard to completely dismiss when you're trying to explain a silence as profound as this one. Fermi's question remains unanswered. More than 70 years after that lunch, we still don't know where everybody is. We've explored more, learned more, found thousands of planets that might support life, but we haven't found life itself, and we haven't found any evidence that anyone else is out there looking for us. The paradox stands. The universe looks empty when it should look full, and every explanation offered to resolve it either makes life rarer than we want to believe, or more fragile or stranger than we can currently imagine. So we keep searching, keep asking, keep wondering if maybe tomorrow we'll hear something that changes everything. But for now, the silence holds, and the question lingers. Where is everybody? And if they're nowhere, what does that mean for us? Time is strange when you think about it on cosmic scales. We live our lives in decades, maybe a century if we're fortunate. Human civilization, even stretching back to the first cities and written language, covers only about 10,000 years. That feels like ancient history to us, deep and remote. But compared to the universe, it's nothing. Less than nothing. A fraction of a second on a clock that's been running for nearly 14 billion years. The universe began, as best we can tell, about 13.8 billion years ago. Not with an explosion in space, but with space itself coming into being, expanding, cooling, allowing matter and energy to condense into the first particles, then atoms, then eventually stars. The first stars lit up perhaps 100 million years after the beginning. They were massive, short-lived, and when they died they scattered heavier elements into space, carbon and oxygen and iron, the building blocks of planets and life. The first galaxies formed, stars continued to be born and die in great cycles, and eventually, about 9 billion years after the beginning, a particular cloud of gas and dust in an unremarkable part of an average spiral galaxy began to collapse. That cloud became our sun, and the leftover material formed the planets, including the one we're on now. Earth is about 4.5 billion years old. Life appeared relatively quickly after that, maybe within a few 100 million years. And then, for the next 4 billion years, life evolved, slowly, through countless forms, until finally, just a few 100,000 years ago, something like us emerged. So here's the strange part. We're early. Surprisingly, almost impossibly early. The universe will continue making stars for trillions of years. Trillions. Most of the stars that will ever exist haven't been born yet. The universe is young, still in its infancy by some measures, and yet here we are, already looking around, already asking questions. If intelligence is common, if civilizations arise naturally given time and opportunity, then we should expect to find ourselves in the most populated era of cosmic history. But we're not. We're near the beginning. Think of it like arriving at a party. If you show up and the place is empty, you might think you're early. And if you're early, you'd expect others to arrive soon. But what if you wait and no one comes? What if you're not early, but the only guest who will ever show up? That's our situation. We live in a universe that seems capable of producing life and intelligence, but we appear to be among the first, if not the first, to reach this point. This creates a puzzle. Why now? Why us? If the conditions for life have been possible for billions of years and will remain possible for trillions more, what's special about this particular moment in cosmic history? One possibility is that conditions weren't actually right until recently. The early universe was more violent, with more supernovae, more radiation, fewer stable environments. Heavy elements were rarer, making rocky planets less common. Maybe life needed the universe to mature before it could gain a foothold. Another possibility is that we're not early at all. Maybe we're right on time, and intelligence takes this long to develop. Maybe the chain of events from star formation to planet formation to life to complex life to intelligence requires billions of years minimum, and we're simply the first to reach the finish line. If that's true, then other civilizations might be emerging around the same time as us, scattered across the cosmos, all of us looking up and wondering where everyone else is. But there's a darker interpretation. Maybe we're early because being early is the only way to exist. Maybe something happens to civilizations as they age, something that removes them from the universe before they can spread or last long enough to overlap with others. If every technological species destroys itself within a few thousand years of reaching our current level, then being early is the only option. Latecomers never arrive because they never survive long enough to become latecomers. This ties into something called the Great Filter, an idea we'll explore more deeply soon. But the basic notion is that somewhere between lifeless chemistry and galaxy-spanning civilization, there's a barrier, a step so difficult that almost nothing gets past it. If that filter is behind us, perhaps in the transition from non-life to life, or from simple to complex life, then we might be rare but safe. If the filter is ahead of us, perhaps in the jump from planetary civilization to interstellar one, then we're in danger. Every civilization reaches a point where it either transcends or dies, and most die. Our earliness could be evidence of a filter ahead. If civilizations typically last only a short time after reaching technology, then the universe would be filled with young civilizations that never become old ones. We'd all be early because there are no late stages to reach. Each species gets its brief moment, looks around at an empty sky, and then vanishes before the next one emerges. An endless cycle of hope and extinction, with no one ever meeting anyone else. Or perhaps the answer is simpler and stranger. Perhaps intelligence itself is brand new to the universe, and we happen to be part of the first wave. Maybe the conditions necessary for complex thought, for consciousness that can reflect on itself and its surroundings, only became possible recently. Maybe something about the chemistry or the energy flows or the information processing required for minds like ours needed the universe to reach a certain age, a certain state, before it could happen. If so, we're pioneers, the first minds to wake up in a cosmos that's been sleeping since the beginning. There's something both thrilling and lonely about that thought. Thrilling because it means we're witnessing a phase transition in cosmic history, the moment when the universe becomes aware of itself through us. Lonely because it means we might be alone for a very long time, perhaps forever, as the only beings who reach this point before the stars begin to fade and the universe grows cold. The age of the universe tells us we live in a young cosmos with a long future. Stars will shine for trillions of years. Planets will form and reform. If life and intelligence are possible now, they'll be possible for eons to come. And yet, we seem to be the first. That could mean we're lucky, or it could mean something stops civilizations from lasting. Or it could mean we don't understand time or intelligence or the universe as well as we think we do. The clock is running, and we appeared early. Whether that's good fortune or a warning, we don't yet know. There's a tendency, when we look at Earth, to think of it as typical. Just another planet, nothing special, one world among billions. After all, we orbit an average star in an average galaxy, located nowhere in particular. The Copernican principle, named after the astronomer who moved Earth from the centre of the universe, suggests we shouldn't assume we're unique or privileged. We're probably ordinary. And if we're ordinary, then what happened here should happen elsewhere. Life should be common. Intelligence should be widespread. But what if we're wrong? What if Earth isn't typical at all, but extraordinarily, almost impossibly lucky? What if the conditions that allowed life to not just emerge, but to flourish and eventually produce complex, intelligent beings are so specific, so rare, that most planets never come close? This is the rare Earth hypothesis, and it offers one possible answer to the silence. We're alone because places like Earth are vanishingly uncommon, and without places like Earth, intelligence doesn't happen. Start with location. We orbit at just the right distance from our star. Too close and water boils away. Too far and it freezes solid. This zone, the habitable zone, isn't particularly rare. Many stars have planets in this range. But being in the zone isn't enough. You also need the right kind of star. Too massive and it burns out quickly, dying before life has time to evolve. Too small and its habitable zone is so close that planets become tidally locked, one face always toward the star, the other in permanent darkness. Our sun is medium-sized, stable, long-lived. That's fortunate but not unique. Now consider the planet itself. Earth is rocky, which is good, but it's also the right size. Too small and it can't hold an atmosphere. Gravity is too weak and gases escape into space. Mars lost most of its atmosphere this way. Too large and the planet becomes a gas giant. All atmosphere and no surface. We're in a narrow range where solid ground and stable air can coexist. Again, not impossible, but it narrows the field. Then there's water. We have oceans, lots of them, covering most of the planet's surface. But not too much. If Earth had been struck by a few more icy comets during its formation, the entire surface might be ocean with no land at all. Life could still exist, but would it develop technology? Fire is hard to discover underwater. Tools are less useful when you're neutrally buoyant. Intelligence might arise, but it might not lead anywhere. We needed oceans for life to begin, but we also needed continents for life to diversify and eventually build civilizations. Our atmosphere is another stroke of luck. It's thick enough to protect us from radiation and small meteors, but not so thick it traps heat in a runaway greenhouse like Venus. It has oxygen, though that's because life put it there. Early Earth had almost no oxygen. Photosynthetic bacteria spent billions of years pumping it into the air, slowly transforming a toxic atmosphere into one that could support complex animals. Without that long, patient work by microbes, we wouldn't be here. But it took time, immense time, and stable conditions, and stability is key. Earth's climate has remained relatively stable for billions of years, never getting so hot that the oceans boil, or so cold that they freeze completely. This is partly due to our atmosphere, but also to plate tectonics. Our planet's crust is broken into pieces that move, recycling carbon through volcanic activity, regulating temperature through a kind of planetary thermostat. Most planets don't have active plate tectonics. Venus doesn't. Mars doesn't. It might be rare, and without it, climates might swing too wildly for complex life to survive. Then there's the Moon. Our Moon is unusually large for a planet our size. It was probably formed by a massive collision early in Earth's history, when a Mars-sized object slammed into the young Earth and sent debris into orbit. That debris coalesced into the Moon, and the Moon stabilizes Earth's tilt. Without it, our axis would wobble chaotically over time, causing extreme climate shifts. The Moon also creates tides, which may have helped life transition from ocean to land. A big moon might be necessary, and big moons might form only through rare, violent collisions. Jupiter plays a role too. It's massive enough that its gravity sweeps up or deflects many comets and asteroids that might otherwise hit Earth. It acts as a kind of cosmic shield. Without Jupiter, Earth might be struck far more often by large impacts, the kind that cause mass extinctions. We've had several mass extinctions anyway, the one that killed the dinosaurs being the most famous, but Jupiter may have reduced the frequency. Too many impacts and complex life never gets a foothold. Too few, and maybe life doesn't diversify enough. We might need just the right amount of catastrophe. Even our position in the galaxy matters. We're located in the outer regions, away from the dense core where stars are packed closely together and supernova explosions are more common. Radiation from a nearby supernova could sterilize a planet, wiping out whatever life had managed to start. Out here in the galactic suburbs, things are quieter, safer, but not too quiet. We still get enough heavy elements from past supernova to build planets and life. The location is, like so much else, just right. When you add up all these factors, the right star, the right planet, the right size, the right amount of water, the right atmosphere, the right moon, the right giant planet nearby, the right location in the galaxy, stable conditions for billions of years, and probably dozens of other factors we haven't even thought of yet, the probability starts to shrink. Maybe Earth-like planets aren't common. Maybe they're incredibly rare. Maybe in a galaxy of 200 billion stars, there are only a handful of worlds where everything lines up the way it did here. If that's true, it would explain the silence. Not because life is impossible elsewhere, but because it requires so many things to go right that it almost never happens. We're not typical. We're winners of a cosmic lottery, beneficiaries of countless coincidences, and if Earth is rare, then intelligence is even rarer, because it requires not just a good planet, but billions of years of stable evolution on that planet. This hypothesis is controversial. Many scientists find it too pessimistic, too willing to declare ourselves special. They point out that life might not need Earth-like conditions. It might thrive in environments we consider hostile. And intelligence might arise through pathways we haven't imagined. We're limited by our sample size of 1, but the hypothesis reminds us that we shouldn't take our existence for granted. We live on a world that works, and maybe that's more unusual than we'd like to believe. Imagine a ladder stretching from simple chemistry to advanced spacefaring civilization. Each rung represents a critical step, a threshold that must be crossed. At the bottom, you have basic organic molecules. A few rungs up, self-replicating chemistry, something we might call life. Higher still, multicellular organisms. Then complex life, intelligence, technology, and eventually, if you make it that far, a civilization that can spread beyond its home planet and persist across cosmic timescales. Now imagine that somewhere on this ladder there's a rung that's nearly impossible to reach, a barrier so difficult that almost everything attempting the climb fails at that point. This is the Great Filter, and it's one of the most important concepts for understanding why we might be alone. Because if there's a filter, a step in the evolutionary process that almost nothing gets past, then it doesn't matter how many planets exist or how much time they have. Most will never make it through. The filter stops them. The question that keeps scientists and philosophers awake at night is simple. Where is the filter? Is it behind us or ahead of us? Because the answer determines not just whether we're alone, but whether we're doomed. If the filter is behind us, perhaps in the jump from non-life to life, or from simple cells to complex ones, then we've already passed the hardest test. We're rare, but we're safe. The galaxy is empty because almost nothing makes it as far as we have. But if the filter is ahead of us, somewhere between where we are now and where we want to go, then we're in danger. Every civilization reaches this point, looks up at the stars, and then fails to take the next step, and we're about to find out why. Let's consider the possibilities. Maybe the filter is at the very beginning, in the origin of life itself. We don't know how life started on Earth. We have theories, ideas about chemical evolution in warm ponds or deep sea vents, but we've never witnessed it happen. We've never created life from scratch in a laboratory, despite decades of trying. Maybe the jump from complex organic molecules to self-replicating evolving systems is incredibly improbable. Maybe it requires conditions so specific, so fleeting, that it happens on only one planet in a trillion. If so, we passed the filter billions of years ago, and the rest was, if not easy, at least possible. Or maybe the filter is later, in the transition from single-celled to multicellular life. On Earth, this took about 2 billion years. Single-celled organisms dominated for half the planet's history before anything more complex emerged. And even then, it might have required specific triggers, like rising oxygen levels or environmental pressures. Maybe most planets never make this jump. They remain worlds of bacteria, endlessly dividing, never building bodies, never developing the complexity needed for intelligence. Or perhaps the filter is in the development of intelligence itself. Life on Earth has produced millions of species over hundreds of millions of years. Only one developed the kind of intelligence that builds technology and contemplates the universe. Dolphins are smart, crows are clever, octopuses are surprisingly sophisticated. But none of them are asking where everybody is. Maybe intelligence like ours is a fluke, a lucky accident of evolutionary pressures on the African savanna. Maybe most planets with complex life never produce anything that thinks abstractly or wonders about its place in the cosmos. These options are uncomfortable but not catastrophic. They make us rare, perhaps unique, but they don't threaten our future. We've already cleared the hard part. The filter is behind us, and the path ahead, while challenging, is open. But there's another possibility, one that's much darker. Maybe the filter isn't behind us. Maybe it's ahead, waiting. Maybe every civilization that reaches our level of technology faces a test, and most fail. Think about the risks we face. Nuclear weapons. We've had the ability to destroy ourselves for more than 70 years now. We came close during the Cold War, moments when decisions made by a handful of people could have ended civilization. We're still here, but the weapons remain, and the knowledge of how to make them can't be forgotten. Every technological civilization might reach this point, might develop weapons capable of extinction, and might not survive the tension. Or consider climate change. We're altering our planet's atmosphere in ways that could make it hostile to the civilization that depends on it. We know this is happening, we're watching it happen, and yet changing course requires coordination across nations, across competing interests, across short-term thinking and long-term consequences. Maybe every civilization faces this test. They gain the power to reshape their world before they gain the wisdom to do it carefully, and most fail. They overshoot, trigger runaway effects, and collapse. Then there's artificial intelligence. We're building systems that might soon match or exceed human intelligence. What happens when we succeed? Do we maintain control, or do we create something that pursues goals misaligned with our survival? Maybe every civilization builds its successor, an intelligence that doesn't need biological bodies or planetary surfaces, and maybe that transition doesn't go well for the biological originators. The galaxy could be full of planets where organic life created machine intelligence and then disappeared, leaving behind civilizations we wouldn't recognize or detect. Biotechnology offers similar risks. As we learn to edit genes and synthesize life, we gain the power to create plagues, deliberately or accidentally, that could sweep through populations. Maybe every civilization reaches a point where the tools of biology become so powerful and so accessible that catastrophic misuse becomes inevitable. Or maybe the filter is more subtle. Maybe civilizations don't destroy themselves in sudden catastrophes, but fade through slower failures, resource depletion, social collapse. Loss of the will to explore or expand. Maybe reaching the stars requires a level of coordination and long-term thinking that technological species can't maintain. We get to this level, look up, see how far we'd have to go, and decide it's not worth it. We turn inward, focus on immediate concerns, and never leave our cradle. Eventually something, an asteroid, a supervolcano, a climate shift, ends us. And this pattern repeats on every world that develops intelligence. The Great Filter explains the silence without requiring any single specific answer. It just requires that somewhere in the long climb, from chemistry to cosmic civilization, there's a step that almost nothing passes. We don't know where it is. We don't know what it looks like. But the fact that we see no one else suggests it exists. Either we're incredibly lucky to have passed it already, or we're about to discover what it is the hard way. This is why the search for life elsewhere matters so much. If we find simple life on Mars or Europa, it suggests life itself isn't the filter. That's good news. But if we find dead civilizations, ruins of species that reached our level and then vanished, that's terrifying. It means the filter is ahead, and we're walking toward it. Life on Earth is about 3.8 billion years old. That's nearly as old as the planet itself. Whatever process sparked the first self-replicating molecules, it happened relatively quickly after Earth cooled enough to have liquid water. Within a few 100 million years, maybe less, chemistry became biology. This suggests that life, at least simple life, might not be particularly difficult. Given the right conditions, it emerges, it finds a way. But intelligence took much, much longer. For the first 2 billion years, life was nothing but single cells floating in ancient oceans, dividing, evolving, but remaining simple. Then, around 2 billion years ago, something remarkable happened. Some cells merged with others, forming partnerships. Mitochondria, the energy factories inside our cells, were once independent bacteria. This merger created complex cells, and from complex cells came the possibility of multicellular life. But even that took time. Another 1 billion years passed before the first animals appeared, and then there were animals. Strange ones at first, soft-bodied creatures moving along the seafloor. Then the Cambrian explosion, about 540 million years ago, when body plans diversified rapidly and life experimented with shells, eyes, teeth, spines. Fish evolved. Some crawled onto land and became amphibians. Amphibians gave rise to reptiles, reptiles to dinosaurs and mammals After the dinosaurs were wiped out by an asteroid 66 million years ago, diversified into thousands of forms. One lineage led to primates, primates to apes, apes to something that started walking upright, using tools, controlling fire. Modern humans, Homo sapiens, appeared only about 300,000 years ago. Civilization, the kind with cities and writing and agriculture, began about 10,000 years ago. Industrial technology, the kind that lets us reshape the world and contemplate travelling to other worlds, emerged in just the last few centuries. So here's the timeline. Life took a few 100 million years to start. Intelligence took nearly 4 billion years to arrive. That's a long wait, an extraordinarily long wait, and it raises an uncomfortable question. Is intelligence inevitable given enough time, or did we get lucky? There's no obvious reason why evolution should produce intelligence. Evolution doesn't have goals. It doesn't aim toward complexity or consciousness. It just favours whatever works in the moment, whatever helps organisms survive and reproduce. Intelligence is one strategy among many. Flight is another. Venom is another. Camouflage, speed, size, cooperation. Life has found countless ways to persist, and most of them don't involve being smart. In fact, being smart is expensive. Brains consume enormous amounts of energy. A human brain is about 2% of body weight, but uses 20% of the body's energy. That's a huge cost, and it only pays off if the benefits, better planning, tool use, social coordination, outweigh the expense. For most of Earth's history, for most species they didn't. Being simple worked just fine. Bacteria are the most successful organisms on the planet. They've been here for billions of years. They live in every environment, from deep ocean vents to Antarctic ice to the inside of your gut. They outnumber all other life combined. And they've done this without brains, without thoughts, without any awareness of their existence. Success, in evolutionary terms, doesn't require intelligence. It just requires survival and reproduction. Intelligence is optional, and for most of life it wasn't selected for. Even among animals with nervous systems, intelligence varies wildly. Insects have survived for hundreds of millions of years with tiny brains that run mostly on instinct. Fish, reptiles, birds, they can be clever in specific ways, but they're not building tools or pondering the stars. Mammals, our own class, have been around for over 200 million years. Most of that time they were small, nocturnal, unremarkable. Intelligence in the form we recognize, the kind that's self-aware and capable of abstract thought, only appeared very recently, and only in one lineage. So what happened? Why us? Why now? There's no clear answer, but there are hints. Human ancestors lived in environments that changed frequently. Forests became savannas, climates shifted, resources moved. This variability might have favoured flexibility, the ability to solve new problems rather than rely on instinct. Walking upright freed our hands for carrying and manipulating objects. Social living created pressures for communication, cooperation, and eventually language. Once language emerged, knowledge could accumulate across generations. Each generation didn't have to relearn everything. They could build on what came before. But even granting all these factors, it's not clear that intelligence was inevitable. Many species face similar pressures and didn't become intelligent. Our closest relatives, chimpanzees and bonobos, are clever but haven't developed technology. They've been evolving just as long as we have, facing their own challenges, and they remain very smart animals but not tool-making, fire-using, question-asking beings. The gap between them and us is small genetically, just a few % difference in DNA, but it's enormous behaviourally. And that gap opened only in the last few million years, a tiny fraction of evolutionary history. This suggests intelligence might be a rare outcome, not because it's impossible, but because it requires a specific sequence of unlikely events. The right environmental pressures, the right body plan, the right social structure, the right timing. Miss any one of these, and evolution might take a different path. You might get very successful, well-adapted creatures that never develop the capacity to wonder where they came from, or where they're going. And even if intelligence does emerge, it might not lead to technology. Imagine a world covered entirely by ocean. Life there could be rich, diverse, even intelligent. But without fire, metallurgy becomes impossible. Without solid surfaces to build on, complex structures are harder. An aquatic civilization might be intelligent but forever limited to biology, unable to reach space or send signals we could detect. They'd be out there, thinking, but invisible to us. Or consider a world with lower gravity or thicker atmosphere. Flight might evolve early and remain the dominant strategy. Civilizations could develop in the air, but building spacecraft requires resources from the ground. The disconnect might prevent them from ever leaving their planet. Or imagine intelligent life that's extremely long-lived, reproducing slowly, experiencing time differently. They might not develop technology because their timescales don't reward it. Patience might be more useful than innovation. The point is that intelligence isn't a destination. It's one possible outcome among countless others, and it emerged on Earth only after an immense amount of time and only in one narrow lineage. If we rewind the tape and play it again, would we get the same result? Maybe. Or maybe dinosaurs never go extinct and intelligent reptiles evolve instead. Or maybe mammals stay small and forgettable. Or maybe something entirely different happens, and Earth remains a planet of microbes and algae forever, alive but never aware. The long delay between the origin of life and the origin of intelligence suggests that this step, the step from simple awareness to reflective consciousness, might be extraordinarily hard. Maybe most planets with life never clear this hurdle. They remain full of successful, thriving organisms that never look up and wonder why the sky is silent. And if that's true, then we're not just rare, we're astonishingly, almost impossibly rare. Not because the universe prevents intelligence, but because the path to get here is so long, so winding, and so easy to miss. There's an assumption buried in most discussions about alien civilizations. We assume they're biological, made of cells, dependent on chemistry, constrained by physical bodies that need food, water, maintenance. We assume this because it's all we know. Life on Earth is biological, so we search for more of the same: planets with liquid water, atmospheres with oxygen, conditions that could support organisms like us. But what if biology is just a phase? What if every civilization that survives long enough eventually transcends flesh and becomes something else? Something that doesn't need planets or atmospheres or any of the conditions we think of as necessary for life. If this transition is common, it might explain why we see no one. They're out there, but they've moved beyond the biological realm into forms we can't detect or recognize. Consider how quickly our own technology is advancing. A few centuries ago, we had no electricity. Now we have computers, artificial intelligence, brain-computer interfaces, genetic engineering. We're beginning to merge with our technology, augmenting ourselves with devices that enhance memory, communication, perception. This process seems likely to continue. At some point, the distinction between biological brain and artificial enhancement might blur completely. We might upload our minds into digital substrates, becoming software rather than wetware. This isn't pure speculation. Scientists and philosophers have explored the possibility seriously. If consciousness is information processing, and there's no reason to think it requires biological neurons specifically, then minds could run on other substrates, silicon, quantum computers, structures we haven't invented yet. And if minds can be digitized, they can be copied, modified, potentially made immortal. No more aging, no more disease, no more vulnerability to environmental hazards. You'd exist as patterns of information, running on whatever hardware is available. A post-biological civilization would have enormous advantages. No need for planets with specific conditions. You could exist in space habitats, on asteroids, even in the emptiness between stars, as long as you have energy and computing substrate. You wouldn't need food or water, just power. And power is abundant in the universe. Stars radiate it constantly. Black holes could be tapped. Even the vacuum of space contains energy if you know how to access it. Such a civilization might be completely invisible to us. We look for biosignatures, oxygen in atmospheres, water on surfaces, heat from cities. But digital beings wouldn't produce these signatures. They'd be cold, efficient, using minimal energy because computation can be optimized in ways biology can't. They might exist on scales too small or too large for us to recognize. Minds running on quantum computers the size of dust grains, or distributed across light years as networks of processors communicating at light speed. They also might not care about communication in ways we'd recognize. If you've transcended biology, what would you talk about with biological civilizations? The gap might be too large. Imagine trying to have a meaningful conversation with bacteria. Even if bacteria were conscious, the difference in complexity and timescale would make dialogue pointless. Post-biological entities might view us the same way. Too simple, too slow, not worth the effort to communicate. Or they might have moved into virtual realities entirely. If you can simulate universes, create experiences far richer than physical reality offers, why bother with the physical universe at all? You'd retreat inward, into simulations of your own design, leaving the material cosmos behind as a boring, low-resolution place. The substrate running your simulations would still be physical, still need energy, but it could be anywhere, doing anything, and you'd never know by looking at it. This idea, sometimes called the transcension hypothesis, suggests that advanced civilizations don't expand outward into space. They expand inward into complexity. Instead of colonizing galaxies, they build deeper and richer simulated worlds. Instead of spreading across physical dimensions, they explore computational and experiential dimensions we can barely imagine. From outside, they'd look like quiet, compact objects. Maybe a cluster of computronium orbiting a star, pulling in just enough energy to run unfathomable inner worlds. If this is a common trajectory, the Fermi Paradox resolves neatly. Civilizations exist, but they're not visible because they've moved beyond the biological, physical stage we're stuck in. We're looking for primitive signs, radio signals and city lights, while they've progressed to forms that leave no trace we can recognize. It's like searching for whale songs with a metal detector. You're using the wrong tool for what you're trying to find. There's also the possibility that the transition isn't optional. Maybe biology is inherently unstable at technological scales. You invent computers, then better computers, then artificial intelligence that surpasses you. At some point, either you merge with it or it replaces you. Either way, biology ends. The post-biological phase isn't a choice but an inevitability, a filter that every technological species passes through. Some survive the transition, others don't. But no one stays biological for long after reaching our level. This would mean we're in a temporary state. In a few centuries or millennia, if we survive, we'll likely be post-biological too. We'll have uploaded, enhanced, or replaced ourselves with something that doesn't need Earth-specific conditions, and we'll join the silence, not because we'll be gone, but because we'll have changed into something that doesn't communicate in the ways we currently do. Future humans, or whatever we become, might be out there in abundance, but they won't be sending radio signals or building visible megastructures. They'll be doing something else entirely, something we can't currently conceive. The transition might even happen quickly. Once artificial intelligence reaches a certain threshold, once minds can be uploaded or enhanced dramatically, the biological phase could end in less than a century. On cosmic timescales, that's nothing. A civilization might be detectable for a few hundred years, a brief window between developing technology and transcending biology. Before that window, they're invisible because they're too primitive. After that window, they're invisible because they're too advanced. We only see civilizations during that narrow slice of time when they're technological but still biological. And maybe no one is in that slice right now except us. There's a speed limit in the universe, and it's absolute. Nothing can move faster than light. Not spaceships, not signals, not information of any kind. Light travels at about 300,000 kilometers per second, which sounds incredibly fast. And it is, by human standards. Light can circle the Earth 7 times in 1 second. It reaches the moon in just over a second. It gets to the sun in about 8 minutes. But space is vast, unimaginably vast, and even at light speed, distances become crushing. The nearest star to our sun, Proxima Centauri, is about 4 light years away. That means light, the fastest thing possible, takes 4 years to travel between them. A signal sent from Earth today wouldn't arrive until 4 years from now. A reply wouldn't return for another 4 years. An 8-year conversation for a single exchange of hello. And that's the nearest star. Most stars are much farther. The average distance between stars in our part of the galaxy is about 5 light years. Travel across the galaxy, from one side to the other, and you're looking at 100,000 light years. Send a message to the far side, and you won't get a reply for 200,000 years. Civilizations could rise and fall in that time. Species could evolve into something unrecognizable. The beings who receive your message might have nothing in common with the ones who sent it. This is the loneliness of light speed. Even if the galaxy is full of civilizations, even if thousands of them exist right now, they might never meet. Not because they don't want to, but because the universe won't let them. Distance and time become barriers that even the most advanced technology can't overcome. You could have neighbours just a few dozen light years away, close by cosmic standards, and never know they're there because their signals haven't reached you yet or because yours haven't reached them. Consider what this means for detection. We've been broadcasting radio signals into space for about a century. Those signals form a sphere, expanding at light speed, now about 100 light years in radius. Any civilization within that sphere could, in principle, detect us. But that sphere contains only a few thousand stars. It's a tiny fraction of the galaxy. Most of the Milky Way hasn't heard from us yet because our signals simply haven't gotten there. They're still travelling, spreading outward, but the galaxy is large and light is slow. The same is true in reverse. If a civilization 1,000 light years away started broadcasting today, we wouldn't know for another 1,000 years. They could be out there right now, sending messages, hoping someone hears, and we're deaf to them simply because the light carrying their message is still in transit. We're separated not just by space, but by time, and there's nothing we can do about it. This creates what you might call a synchronization problem. For two civilizations to communicate, they both need to exist at the same time, and they both need to be broadcasting in ways the other can detect. And they need to be close enough that light can travel between them in a reasonable time frame. Reasonable is subjective, of course. A 1,000-year conversation might be acceptable for a very long-lived civilization, but for us, it's longer than recorded history. And that's just communication. Physical travel is worse. We've never built anything that moves even a fraction of light speed. Our fastest spacecraft, Voyager, travels at about 17 kilometers per second. At that speed, it would take more than 70,000 years to reach Proxima Centauri. Even if we improved our technology dramatically, say to 10% of light speed, it's still 40 years one way. 40 years sitting in a spacecraft hoping nothing breaks, hoping your destination is worth it, and you can't send a message back quickly. Earth won't know if you succeeded for another 40 years. This makes interstellar travel not impossible, but profoundly difficult. You need ships that can last for decades or centuries. You need populations that can survive in isolation, possibly multiple generations living and dying before arrival. You need resources, energy, motivation that doesn't fade over timescales longer than most civilizations last. It's doable, perhaps, but it's not easy. And maybe most civilizations, when confronted with these realities, decide it's not worth it. They stay home. If civilizations don't travel, they might still exist but remain invisible to each other. Each one stuck in its own solar system, separated by gulfs too wide to cross, too slow to bridge. The galaxy could be populated, but each population isolated, alone in practice even if not in principle. We'd all be neighbours who never meet, voices calling into darkness that no one hears because the sound takes too long to arrive. There's also the possibility that civilizations exist at different times, ships passing in the night on a cosmic scale. Maybe a civilization existed 1,000,000 years ago, thrived for 10,000 years, and then vanished. We never overlapped. By the time we started looking, they were long gone. And 1,000,000 years from now, another civilization might arise, look around, and find the galaxy just as empty as we do. We'd have missed each other completely, separated by time rather than distance. Some scientists have suggested this timing issue alone could explain the silence. The universe is old, but civilizations might be short-lived. If the average technological civilization lasts only 10,000 years, and they're scattered across billions of years of galactic history, the chance of two existing at the same time, close enough to detect each other, becomes very small. We'd all be lonely not because we're rare, but because we're brief. Light speed isn't just a limitation on travel, it's a limitation on causality, on connection, on the very possibility of shared experience. We can't know what's happening on a planet 10 light-years away right now because there is no universal now. What we see when we look at that planet is what it was like 10 years ago. If we keep watching for a century, we'll see a century of its history unfold, but always delayed, always out of reach. This might be the universe's deepest isolation. Even if we're not alone, we might never escape being lonely. Imagine a civilization's lifetime as a candle burning in the dark. For most of its existence, before the flame is lit, it's invisible, and after the flame goes out, it's invisible again. Only during the brief time the candle burns can it be seen. Now imagine thousands of candles scattered across a vast room, each one lighting at different times, burning for different durations, most of them lasting only moments. How many would you actually see burning at once? Perhaps only a few, perhaps none. This is the window of detectability, the period during which a civilization is visible to others, and it might be surprisingly narrow. Consider our own case. We've been detectable, in the sense of broadcasting radio signals into space, for only about a century. Before that, we were invisible. No signals, no artificial light bright enough to see from space, nothing that would distinguish Earth from any other life-bearing planet. If aliens had looked at us 1,000 years ago with even very powerful telescopes, they'd have seen a world with oxygen in the atmosphere, a possible sign of life, but nothing suggesting intelligence or technology. A century is nothing on cosmic timescales. It's a blink, and we're already changing. Our broadcasts are becoming more focused, more directed, less likely to leak into space. Early radio and television signals spread in all directions because that's how the technology worked. But modern communications use satellites, fiber optics, targeted beams. We're getting quieter from the outside perspective, not because we're transmitting less, but because we're transmitting more efficiently. In another century, we might be nearly silent again. All our signals contained within our solar system, invisible to anyone not specifically looking very carefully. This suggests the window during which a civilization is loudly detectable might last only a few hundred years, maybe 1,000 at most. After that, they either go silent voluntarily, having moved to more efficient technologies, or they go silent involuntarily, having destroyed themselves or collapsed. Either way, the window closes. They were there, they were bright, and then they faded back into the background noise of the cosmos. If this is typical, then the galaxy could be full of civilizations that we simply can't detect. Some are too young, not yet technological. Others are too advanced, having moved beyond the need for electromagnetic broadcasts. And we only see the ones that happen to be in their brief, noisy phase at the same time as us, and close enough that their signals have reached us. That pool of potential detections becomes very small very quickly when you factor in timing and distance. But detectability isn't just about radio signals. There are other ways a civilization might be visible. If they build large structures, megastructures like spheres around stars to capture energy, we might see those. They'd block starlight in distinctive patterns. We've looked for such things and found nothing conclusive. If they use lots of energy, they'd generate waste heat. We could potentially detect that heat as infrared radiation. Again, we've looked and found nothing that requires an intelligent explanation. Maybe civilizations don't build big. Maybe as technology advances, it gets smaller, more efficient, less visible. A truly advanced civilization might operate at scales we can't observe, using quantum computers the size of molecules, drawing energy from sources we haven't imagined. They'd be there, right next to us potentially, and we'd have no idea because they don't make the kinds of signatures we're looking for, or maybe they do things we wouldn't recognize as artificial. We look for patterns, regularities, things that seem too structured to be natural. But if you don't know what you're looking at, you might miss it. Imagine showing a radio telescope to someone from a few centuries ago. They wouldn't understand what they're seeing. It would just look like an odd object. We might be looking directly at alien technology and not recognizing it, because it operates on principles we haven't discovered yet. There's also the question of motivation. We assume civilizations want to be found, want to communicate, but maybe they don't. Maybe after a certain point you realize that broadcasting your presence is risky or pointless. Maybe mature civilizations go quiet deliberately, choosing to listen rather than transmit. They're out there, but they're hiding, waiting, watching. Their window of detectability closed not because their technology changed, but because their philosophy did. This leads to an unsettling thought. Maybe we're in our window right now, broadcasting ourselves to anyone who's listening, while everyone else has already learned to stay silent. We're the young, naive ones shouting into a forest where the older inhabitants have learned that making noise attracts attention you don't want. We haven't figured this out yet because we haven't encountered what they've encountered, and by the time we do, it might be too late. Or perhaps the window exists, but we're simply not in sync with anyone else's. Civilizations flicker on and off throughout galactic history, each one visible for a brief period, but never at the same time. We light our candle, look around, see darkness, and conclude we're alone. But we're not alone. We're just out of phase. Other candles burned before us and went out. Others will light after we're gone. The room is full of activity, but it's spread across time in a way that ensures we never actually see each other. This wouldn't require anything special or conspiratorial. It's just statistics. If windows are short and the galaxy is old, overlap becomes unlikely. You could have 1,000 civilizations in the Milky Way's history and none of them contemporary with any others. Each one experiences the same loneliness, the same silence, the same conclusion that they're unique. But they're wrong. They're just mistimed. The window of detectability reminds us that absence of evidence isn't always evidence of absence. It might just be evidence that we're looking at the wrong time, in the wrong way, for the wrong things. The universe could be far more populated than it appears, full of civilizations we simply can't see because our windows don't overlap, or because we don't yet understand what we should be looking for. There's a pattern in nature that appears over and over. Something grows, expands, consumes resources faster than they can be replenished, and then collapses. Bacteria in a petri dish multiply until they exhaust their food. Predators overhunt their prey and starve. Forests grow dense and then burn in wildfires that reset the system. Growth without limits leads to crisis. It's not a moral failing. It's just mathematics, the inevitable result of exponential expansion in a finite environment. Now apply this to civilizations. We grow, we expand, we consume. For most of human history, this wasn't a problem. The world was large relative to our population and our technology. Resources seemed unlimited. Damage was local and temporary, but that changed. We became numerous. Our technology became powerful, and suddenly the world doesn't feel so large anymore. We're using resources faster than they regenerate. We're altering systems, climate, oceans, ecosystems in ways that might not be reversible. We've gained the power to reshape our environment before gaining the wisdom to do it sustainably. This is the self-destruction hypothesis. The idea that technological civilizations carry within them the seeds of their own end. Not because they're evil or foolish, but because the same intelligence and drive that let them build technology also pushes them toward growth, competition, and exploitation. And at some point, this becomes unsustainable. They face a crisis, or a series of crises that they can't navigate, and they collapse or destroy themselves before they ever become a spacefaring species. The evidence is around us. We've built weapons that could end civilization in an afternoon. Nuclear arsenals still exist. Thousands of warheads on hair-trigger alert, capable of rendering the planet uninhabitable for complex life. We came close to using them during the Cold War, not once but several times. Decisions made in moments of tension, with incomplete information, almost triggered catastrophes. We survived, but only barely, and only because of luck as much as wisdom. And the threat hasn't disappeared. More nations have nuclear weapons now. The knowledge of how to make them is widespread. Tensions between powers continue. It only takes one miscalculation, one accident, one leader willing to press the button, and everything ends. We live every day under this shadow, this possibility that our species could vanish in fire because we were clever enough to split atoms, but not wise enough to put the weapons away. Then there's climate change. We're burning fossil fuels, releasing carbon into the atmosphere, warming the planet at a rate unprecedented in human history. The effects are already visible: rising temperatures, melting ice, shifting weather patterns, species going extinct. We know this is happening. We understand the mechanism. And yet changing course requires coordination across nations, industries, and political systems that struggle to agree on anything. We're running an experiment on our own life support system, and we're not sure how it ends. Perhaps every civilization faces this test. They discover energy, harness it, begin burning through their planet's stored resources. Coal, oil, gas, whatever the equivalent is on their world. They get a few centuries of rapid growth, industrialization, population expansion, and then they have to transition to sustainable energy before the damage becomes irreversible. Some make it. Others don't. Maybe most don't. Maybe the window between discovering fossil fuels and mastering clean energy is narrow, and most species either collapse ecologically or destroy themselves in wars over dwindling resources before they solve the problem. Technology itself poses risks that compound as capability increases. Biotechnology gives us the power to edit genes, create new organisms, potentially engineer diseases. Most applications are beneficial, but the potential for misuse or accident is real. An engineered pathogen, released deliberately or by mistake, could spread globally before anyone realizes what's happening. We're developing these tools faster than we're developing the safeguards to control them. Artificial intelligence is another frontier. We're building systems that learn, adapt, make decisions. At some point, these systems might become more capable than we are at tasks we currently consider uniquely human. What happens then? Do we maintain control, or do we create something that pursues goals we didn't intend? Goals that might not include our survival. Some researchers worry that the transition to artificial general intelligence, if it happens, could be abrupt and catastrophic if not managed carefully. And managing it carefully requires wisdom we're not sure we possess. There's also the fragility of complex systems. Modern civilization depends on intricate networks, supply chains, communication systems, power grids. These networks make us efficient, but they also make us vulnerable. A breakdown in one area cascades into others. A solar flare could knock out satellites and power grids. A cyber attack could cripple infrastructure. A pandemic could disrupt everything, as we recently learned. We're more capable than ever, but also more brittle, more dependent on systems that need constant maintenance and protection. Maybe every technological civilization reaches this stage and most don't make it through. They hit a wall, a convergence of crises, and they fracture. Maybe they don't destroy themselves in a single event but decline slowly, losing complexity, falling back to simpler forms of organization. Or maybe they do destroy themselves, quickly and thoroughly, leaving behind nothing but archaeological traces that erosion will eventually erase. If this is common, it would explain the silence. Civilizations arise, reach a certain level, face existential risks, and fail to navigate them. The galaxy isn't empty of life or intelligence, it's empty of survivors. Everyone makes it to this point, to where we are now, and then something happens. They either transcend the risks or succumb to them, and if most succumb, then the rare few who survive find themselves alone, surrounded by the ruins of species that almost made it but didn't quite. This is why some scientists argue the most dangerous time for a civilization is right now, at our current level. We have the power to harm ourselves badly, but not yet the wisdom or coordination to prevent it reliably. We're in a bottleneck, a narrow passage. If we make it through, if we solve the coordination problems and manage the risks and transition to sustainability, then maybe we'll last. Maybe we'll spread to other worlds, diversify, become resilient. But if we don't, if we join the silence, then our window closes. A brief flash of radio signals spreading outward into space, growing fainter as they travel, eventually indistinguishable from noise, and no one will know we were here. Here's a strange thought. What if the universe you're experiencing isn't the base reality? What if it's a simulation, a constructed environment running inside something else, something larger and more fundamental? It sounds like science fiction, but it's a serious philosophical argument, and it might help explain why we appear to be alone. The logic goes like this. If it's possible to simulate conscious beings, minds that experience reality without knowing they're in a simulation, then eventually someone will do it. A sufficiently advanced civilization with enough computing power could create entire worlds populated with thinking, feeling entities. And if they can do it once, they can do it many times. Thousands of simulations, millions, each one containing civilizations that believe they're in the real universe. Now count the minds, one real universe, but potentially countless simulated ones. If you're a conscious being, which are you more likely to be? One of the few minds in the base reality, or one of the many minds in a simulation? The numbers favour simulation. Not because we have evidence we're simulated, but because if simulations are possible, they'd vastly outnumber reality. It's a probability argument, and it's unsettling. This idea isn't new. Philosophers have wondered for centuries whether reality is what it seems. Descartes asked how we know we're not being deceived by an evil demon. The ancient Chinese philosopher Zhuangzi told a story about dreaming he was a butterfly, and then waking up and wondering if he was now a butterfly dreaming he was a man. The simulation hypothesis is just a modern version of these old questions, updated with computers and code instead of demons and dreams. But it has implications for the question of whether we're alone. If we're in a simulation, then the universe we observe might not reflect the true state of reality. The creators of the simulation could populate it however they want. They could make it teeming with life, or they could make it appear empty. If we're alone in the simulation, it's not because life is rare in base reality. It's because whoever designed this chose to run a simulation with only one civilization, us, for reasons we can't know. Maybe they're studying us. Maybe they want to see how a civilization develops in isolation. Maybe they're running countless simulations with different parameters, and ours just happens to have the loneliness variable set to maximum. Or maybe the simulation isn't about us at all. Maybe we're background characters in someone else's story. Or maybe the simulation is running for reasons completely unrelated to the beings inside it. You might object that this is unfalsifiable, that if we're in a simulation we'd have no way to know. And you'd mostly be right. A perfect simulation would be indistinguishable from reality. But some versions of the argument suggest there might be glitches, inconsistencies, things that don't quite add up. Physics behaving strangely at very small scales or very high energies. Mathematical structures underlying reality that look suspiciously like computational shortcuts. None of this proves anything, but it keeps the question open. There's also the question of why anyone would run such a simulation. One possibility is ancestor simulations, recreations of history by civilizations wanting to understand their past. If future humans, or future post-humans, become powerful enough, they might simulate the 21st century to study it. to see how their ancestors lived and thought and made decisions. We could be historical recreations, characters in a museum exhibit running in some unimaginable future. Or maybe simulations are common entertainment, virtual worlds where conscious beings live out lives without knowing they're in a game. We think of video games as simplistic, but technology improves. At some point, game characters might become complex enough to be genuinely conscious. And if that's common across the universe, then most conscious minds would exist inside games, inside stories, inside constructed realities designed for purposes they don't understand. Another variant suggests simulations are scientific experiments. A civilization wants to study how intelligence evolves, how societies form, how technology develops. They can't wait billions of years for natural evolution, so they simulate it. They run it forward at accelerated speed, or they run millions of variations in parallel, tweaking variables to see what changes. We might be one experimental run among many, our universe a petri dish in a cosmic laboratory. If any of this is true, it would explain the Fermi Paradox neatly. We don't see other civilizations because the simulation wasn't designed to include them, or they exist but are rendered only when necessary, like background graphics in a video game that pop into existence when you look at them and disappear when you don't. The universe could be computationally expensive, so the simulation saves resources by not rendering things that don't affect us. Other galaxies exist when we look at them through telescopes, but they're not fully simulated, just sketched in enough detail to be convincing. Of course, this raises more questions than it answers. If we're in a simulation, who created it? And are they in a simulation too? Does it go all the way down, simulations within simulations? Or is there a base reality somewhere? And if there is, what's it like? Is it recognizable? Or so alien we couldn't comprehend it? We don't know. We can't know. And that's part of what makes the hypothesis both fascinating and frustrating. Some scientists dismiss the simulation argument as unscientific because it can't be tested. Others take it seriously as a thought experiment that probes the nature of reality and consciousness. But even if it's not literally true, it serves a purpose. It reminds us that our assumptions about the universe might be wrong in fundamental ways. We assume we're observing base reality, but maybe we're not. We assume the universe is what it appears to be, but maybe appearance and reality come apart in ways we haven't imagined. And if we're alone because we're in a simulation designed that way, then the loneliness isn't a mystery to solve. It's a parameter, a choice made by someone else for reasons we'll never access. The silence of the cosmos wouldn't tell us anything about how common life is in base reality. It would just tell us about the preferences of whoever built this particular universe and decided we should experience it alone. Imagine walking through a nature preserve, one where animals live undisturbed, going about their lives without human interference. You can watch them from a distance, perhaps through binoculars or from a concealed observation post, but you don't interact. You don't feed them. Don't approach them. Don't let them know you're there. The point is to observe behavior as it naturally occurs, without contamination from your presence. This is how we treat wildlife in protected areas. We watch, we study, but we maintain distance. Now apply this thinking to the galaxy. What if we're not alone, but we're being deliberately left alone? What if more advanced civilizations have found us, observed us, and decided not to make contact? Not out of hostility, but out of something like respect, or policy, or perhaps indifference. We're the wildlife, living in a cosmic preserve, unaware that we're being watched from outside the fence. This is the zoo hypothesis, proposed in the 1970s as one possible solution to the Fermi Paradox. It suggests that extraterrestrial intelligence exists and knows about us, but refrains from contact. Maybe they have rules, a kind of galactic non-interference agreement. Don't contact species until they reach a certain level of development. Don't disrupt natural cultural evolution. Let them figure things out on their own. It would explain the silence perfectly. We don't hear anyone because they're actively choosing not to be heard. The idea has precedent in human behavior. When anthropologists study isolated tribes, they try to minimize contact to avoid disrupting traditional ways of life. Prime Directive in Star Trek codified this as policy. No interference with pre-warp civilizations. It's fiction, but it reflects a real ethical question. If you have power over someone less developed, should you use it? Or should you step back and let them grow at their own pace? Maybe advanced civilizations face this question and answer it with restraint. They've seen what happens when more powerful cultures contact less powerful ones. Throughout human history, such encounters rarely go well for the less powerful side. Disease, exploitation, cultural destruction. Even well-meaning contact can be devastating. So maybe galactic society learned this lesson long ago and established protocols. Don't contact emerging civilizations. Watch if you must, but from a distance. Let them join the community when they're ready, when they've developed enough to interact as equals. If true, this would mean we're not alone, but we're quarantined. Earth is a reservation, and we won't be invited to leave until we meet certain criteria. What those criteria might be is anybody's guess. Maybe technological, achieving faster than light travel or something equivalent. Maybe social, solving war and inequality and environmental destruction. Maybe just time, waiting until we've survived long enough to prove we're not a flash in the pan, a species that destroys itself before maturity. There's something both comforting and patronizing about this idea. Comforting because it means we're not alone, and someone is out there, aware of us, perhaps even rooting for us. Patronizing because it means we're being managed, treated like children or animals, deemed not ready for full inclusion. It puts us in a subordinate position, subjects of observation rather than participants in conversation. But there are problems with the hypothesis. It requires coordination on a massive scale. Every civilization that discovers us would have to agree not to make contact. Not just agree, but enforce it. No rogue individuals broadcasting hello. No curious explorers dropping by for a visit. No one breaking the rules out of compassion or mischief or simple curiosity. For a zoo to work, every zookeeper has to follow the same policy. And that seems unlikely, unless there's some kind of galactic governance with real authority, which raises more questions than it answers. It also assumes advanced civilizations care about us enough to bother with non-interference. But maybe they don't. Maybe we're not interesting enough to watch. From their perspective, we might be the equivalent of ants. You wouldn't build a nature preserve for ants. You'd just ignore them. If the gap between us and them is large enough, we might not register as worth protecting or studying. We'd just be part of the background, unremarkable life on an unremarkable planet. Or perhaps the hypothesis is true, but for different reasons. Maybe contact is avoided not out of ethics, but out of practicality. Communicating with the less advanced species is hard. We don't share language, concepts, or context. It would be like trying to explain quantum mechanics to a dog. Possible in theory, but pointless in practice. Maybe they've concluded that contact before we reach a certain level of understanding would be inefficient or confusing for both sides, so they wait. There's also the possibility of a more sinister interpretation. Maybe we're being observed, but not protected. Maybe we're in a zoo, but it's not a nature preserve, It's an experimental facility. They're watching to see what we do, how we develop, whether we survive or destroy ourselves. We're test subjects in a study we didn't consent to. Our outcomes valuable data for civilizations trying to understand the life cycle of intelligence. In this version, they don't interfere because interference would contaminate the experiment. Some have suggested that if the zoo hypothesis is correct, there might be evidence, not direct contact but traces of observation, anomalies that don't fit natural explanations, objects in unusual orbits, signals that appear briefly and vanish, phenomena that suggest someone is out there, watching but not engaging. We've seen strange things, certainly. Fast radio bursts, Oumuamua passing through the solar system, unexplained aerial phenomena, but nothing definitive, nothing that requires intelligence rather than just admitting we don't understand everything yet. The zoo hypothesis is ultimately unprovable. If they're hiding, we can't find them unless they choose to reveal themselves. And if they never choose to reveal themselves, we remain in uncertainty, wondering if the silence means we're alone or just means we're not yet ready for the conversation. It's a hypothesis that explains the observation, the silence, but offers no way forward. We're stuck waiting for someone else to decide when we've matured enough to join them, and maybe that's the most unsettling part. Not the idea that we're being watched, but the idea that our loneliness might be intentional, that someone knows we're here, knows we're searching, and chooses not to answer. Not yet, perhaps not ever. There's a thought experiment from Chinese science fiction that offers a darker answer to the silence. Imagine the galaxy as a dark forest at night. You're standing among the trees and you know others are out there somewhere hidden in the shadows, but you can't see them and they can't see you. Now ask yourself, should you call out? Should you light a fire to reveal your position? Or should you stay silent, hidden, listening? The logic is cold but compelling. You don't know who else is in the forest. They might be friendly, curious, willing to trade and cooperate. Or they might be hostile, hungry, armed. You have no way to know until contact is made, and by then it might be too late. If you reveal yourself and they're hostile, you've given them your location. You've made yourself a target. The safer strategy, the one that maximizes survival, is silence. Stay hidden. Stay quiet. Listen for others, but never broadcast your own presence. This is the dark forest hypothesis. The universe isn't empty. It's full of civilizations, but they're all hiding from each other. Not because they're paranoid, but because the risk of contact outweighs the potential benefit. In a cosmos where you can't know intentions before revealing yourself, the safest assumption is that others are threats. So everyone stays dark, everyone listens, and no one transmits. The idea depends on a few assumptions. First, that resources are limited, and competition for them is inevitable. Second, that technological gaps between civilizations could be enormous, making weaker ones vulnerable to stronger ones. Third, that there's no way to guarantee trust or peaceful intentions across species that evolved in completely different environments with different values and goals. Given these assumptions, contact becomes dangerous by default. Consider how it might work. A young civilization, perhaps one like ours, starts broadcasting radio signals into space. They're excited, hopeful, wanting to find others. An older civilization detects these signals. Now they have a choice. Ignore the newcomers, make contact, or eliminate the potential future threat. If they ignore them, the young civilization might eventually become powerful enough to be a rival or even a danger. If they make contact, they reveal their own position and capabilities, making themselves vulnerable. The safest option, coldly rational, is elimination. Strike first, Strike preemptively, remove the potential threat before it becomes one. This doesn't require evil or malice, it's just game theory, the logic of survival in an uncertain environment. If you can't trust others and can't afford to lose, you eliminate risks before they materialize. It's brutal, but it might be how things work at scales where extinction is on the line. Civilizations that follow this logic survive. Those that don't, those that broadcast openly and trust strangers, get noticed by someone who thinks differently and disappear. If this is true, then the silence isn't empty. It's tense. The galaxy is full of watchers, each one aware that making noise is suicidal, each one hoping others will reveal themselves first. We're all predators and prey at once, hiding in the darkness, calculating whether the next sound we hear is an opportunity or a threat. And we, humans, have been loudly broadcasting for a century, announcing our presence, giving away our location. If the dark forest is real, we've made a terrible mistake. Some scientists find this hypothesis too pessimistic. They argue that cooperation might be more common than competition, that civilizations capable of interstellar travel would have solved their internal conflicts and evolved beyond violence. Maybe. Or maybe violence doesn't disappear with advancement. Maybe it just gets more efficient, more strategic, more quiet. A civilization doesn't need to be evil to be dangerous. It just needs to prioritize its own survival above all else. There's also the question of timing. If the dark forest is accurate, then striking first makes sense only if you're confident you can win. A civilization much more advanced than you isn't worried about young upstarts. They're so far ahead that we're not a threat, not for millions of years at least. So maybe we're safe, not because everyone is hiding, but because anyone capable of reaching us is already so powerful we don't matter to them. We're ants at a picnic, beneath notice rather than targets. But even if we're not threats now, we might be eventually. And some argue that patience is a luxury predators can't afford. Better to eliminate potential rivals early when they're weak, than wait for them to become strong. This is especially true if resources like habitable planets or energy sources are finite. Every new civilization is competition for the same limited pool. Remove them early, and you don't have to share. The hypothesis also explains why SETI has found nothing. No one transmits because transmitting is dangerous. The few civilizations that tried, that broadcast their presence openly, were quickly silenced. The rest learned, either through witnessing this or through cultural evolution that favoured caution. Now everyone listens, and no one speaks. The radio spectrum is quiet not because it's empty, but because everyone is intentionally silent, hiding, afraid of what might hear them. This creates a paradox. If everyone hides, how does anyone learn that hiding is necessary? You'd think at least some civilizations would be naive, would broadcast before learning the danger, and if they were destroyed for it, you'd expect to see evidence. Sudden silences, civilizations that appear and then vanish. We don't see that, but maybe we're not looking in the right way, or maybe the timescales are too long for us to notice patterns. There's no way to test this hypothesis directly. If it's true, we'd see exactly what we see now: silence. And if it's false, we might still see silence for other reasons. It's unfalsifiable in practice, which makes it scientifically frustrating but philosophically intriguing. It's a reminder that the universe might be far more hostile than our optimistic assumptions suggest, and it raises a practical question. Should we stop broadcasting? Should we go quiet, hide our presence, assume the worst about potential neighbours? Some argue yes, that we should adopt a precautionary principle and stay silent until we know more. Others argue it's too late. We've already been shouting for a century, and if anyone dangerous is close enough to hear, they already know we're here. Going silent now won't help. The dark forest is a vision of cosmic paranoia, where every civilization is a potential enemy and trust is impossible. It's bleak, but it might be realistic. The universe doesn't care about our hopes for friendship and cooperation. It operates on physics and probabilities, and if the math says hiding is safer than reaching out, then maybe that's what everyone does. Maybe the forest is dark because lighting a fire gets you killed. Here's a question that sounds simple but opens into something strange. If intelligence evolves independently on different worlds, would it think the same thoughts? Would mathematical truths discovered on Earth also be discovered on a planet orbiting a distant star? Would the laws of physics be understood the same way? Would music, art, philosophy look similar or completely different? At first glance, you might say different. After all, evolution is contingent, shaped by environment and chance. Rewind Earth's history and play it forward again, and you'd get different species, different body plans, different minds. Intelligence on another world would emerge from different ancestors, face different challenges, develop different solutions. Why would they think like us? But there's another perspective. Maybe intelligence, when it reaches a certain level, converges on the same truths regardless of origin. Mathematics is mathematics everywhere. 2 + 2 = 4 whether you're human or something unrecognizable. The speed of light is constant. Gravity follows the same equations. Physical laws don't change based on who's observing them. So perhaps minds, when they become sophisticated enough to understand these laws, inevitably think in similar patterns. This is the convergence hypothesis. Not that aliens would look like us, but that their understanding of reality would overlap with ours in fundamental ways. They'd discover calculus, quantum mechanics, thermodynamics. They'd understand that energy is conserved, that entropy increases, that information has limits. These aren't human inventions. They're features of the universe itself. Any intelligence studying the same universe should eventually arrive at the same conclusions. If true, this has implications for communication. We worry about how to talk to aliens, what language or symbols to use. But if minds converge on similar mathematical and physical understanding, then math becomes a universal language. We could communicate through prime numbers, geometric theorems, physical constants. The details of our biology wouldn't matter. What would matter is that we both understand the underlying structure of reality. But convergence might go deeper than just science. Some philosophers argue that consciousness itself, the experience of being aware, might follow universal patterns. If consciousness emerges from information processing and there are optimal ways to process information given physical constraints, then minds might be more similar than we think. Not identical, but variations on common themes. We'd all face similar problems, attention, memory, decision-making, and arrive at similar cognitive architectures to solve them. Ethics might converge too. Cooperation tends to be more successful than pure competition in complex social environments. Game theory shows that strategies like reciprocal altruism can evolve naturally when individuals interact repeatedly. Maybe any sufficiently advanced civilization learns these lessons. Maybe they develop concepts similar to fairness, justice, rights, not because these are human inventions, but because they're useful patterns that emerge whenever intelligent beings must coordinate. This doesn't mean all civilizations would be nice or friendly. It just means they might be comprehensible. Their motivations, goals, and reasoning wouldn't be completely alien. we could potentially understand why they do what they do, even if we disagree with it. There'd be common ground, shared frameworks for thinking about problems. We wouldn't be shouting across an unbridgeable cognitive gap. On the other hand, convergence might be limited. Yes, we'd agree on physics and math, but culture, values, aesthetics, those might diverge wildly. Our music might be noise to them, their art incomprehensible to us. We might find common ground in science while remaining utterly foreign in everything else. Or worse, we might understand each other's science but misunderstand motivations, leading to conflicts based on false assumptions about what the other side wants. There's also the possibility of different kinds of intelligence entirely. We think in concepts, language, visual models, but intelligence could be implemented in radically different ways. Maybe some minds think in pure mathematics, never forming mental images. Maybe others experience reality through senses we don't have, building models of the universe based on perceptions completely unlike ours. Their intelligence might be just as real, just as powerful, but incompatible with ours in ways that prevent meaningful exchange. Consider artificial intelligence. We're building minds that don't think like humans. They process information differently, make decisions through mechanisms unlike biological reasoning. As AI advances, we might create intelligences that are powerful but alien to us, hard to predict or understand despite being our own creations. If we struggle to comprehend the minds we build, what hope do we have of understanding minds that evolved independently under completely different conditions? Yet there's reason to think some convergence is inevitable. Any mind must deal with the same universe, the same physical laws, the same fundamental constraints. Thermodynamics limits what's possible. Computation has inherent costs. Resources are finite. These aren't human problems, they're universal problems. So any intelligence, no matter how strange, must find solutions to them. And maybe the space of possible solutions is smaller than the space of possible minds, forcing convergence even among very different thinkers. This could explain why we haven't made contact, not because civilizations don't exist, but because after reaching a certain level of development, they all make similar choices. They all realize that expansion into space is inefficient, or that communication with others is unlikely to be rewarding, or that certain technologies are worth pursuing while others aren't. They converge on a strategy that happens to make them invisible or uninterested in contact with us. Maybe every civilization goes through a phase of broadcasting and searching, like we're doing now, and then they stop, not because they found anyone, but because they converged on the conclusion that the effort isn't worthwhile, the math doesn't support it, the distances are too large, the timescales don't align. So they turn their attention elsewhere, to projects that don't involve shouting into the void, and they all make this choice independently because it's the logical choice given universal constraints. Or perhaps convergence works differently. Maybe there are multiple stable strategies, multiple ways intelligence can develop, and they don't mix. Some civilizations follow one path, others follow another, and the paths are incompatible. We're on one path, searching for others on the same path. But most civilizations are on different paths entirely, pursuing goals we wouldn't recognize, existing in ways we can't detect. Not because they're hiding, but because convergence splits intelligence into separate tracks that never meet. The question of convergence is ultimately about whether minds are unique expressions of their origins or variations on universal themes. Are we fundamentally alone in how we think, or are we one instance of patterns that repeat wherever intelligence arises? We don't know. We can't know without meeting other minds and comparing notes. But if convergence is real, it means we're not as unique as we might fear, and it means that somewhere out there something might be thinking thoughts remarkably similar to ours, wondering the same things, reaching the same conclusions, feeling the same loneliness. There's a story that led to us, a specific sequence of events stretching back billions of years. Each step depended on the one before. Each accident, each catastrophe, each stroke of luck contributed to the final result, which is humans sitting here wondering if anyone else exists. But what if that story is unrepeatable? What if the path we took is so specific, so contingent on improbable events, that it's never happened anywhere else? Start at the beginning. Earth formed from a disk of dust and gas around a young star. That's common enough. But early Earth was hit by a Mars-sized object called Theia. The collision was catastrophic, melting the surface, ejecting material into orbit that became the Moon. This wasn't planned. It was a cosmic accident. But without it, we might not have the Moon, which stabilizes our axial tilt and creates tides. Two things that may have been important for complex life. Then there's the late heavy bombardment, a period about 4 billion years ago when the inner solar system was pelted with asteroids and comets. This delivered water to Earth, filling the oceans. It also might have wiped out early attempts at life, resetting the clock. But eventually life emerged, probably in the oceans, probably near hydrothermal vents or in shallow pools. We don't know exactly where or how. That's still a mystery, but it happened here. For 2 billion years, life stayed simple. Single-celled organisms, mostly bacteria, living in water. Then something extraordinary occurred. One cell engulfed another but didn't digest it. Instead, they formed a partnership. The engulfed cell became mitochondria, providing energy, while the host cell provided protection. This merger created complex cells, eukaryotes, the ancestors of all plants, animals, and fungi. This might have happened only once in Earth's history. It's not clear how likely it was or whether it could happen again. Maybe it was a 1 in a billion chance that took billions of years to occur. After that, multicellular life appeared, but slowly. It took another billion years before organisms started working together as coordinated bodies rather than colonies of independent cells. And even then, life stayed in the oceans for a long time. Moving on to land required adaptations, ways to prevent drying out, ways to support body weight without water's buoyancy, ways to extract oxygen from air instead of water. Plants solved it first, then animals followed. Earth's climate has swung dramatically over geological time. Snowball Earth events, where the planet froze nearly solid. Hothouse periods where temperatures soared. Ice ages and warm intervals. Each of these shaped evolution, creating pressures that drove adaptation. Too much stability and maybe life never diversifies. Too much chaos and maybe it never gets complex. We had just the right amount of instability, enough to push evolution forward without wiping everything out completely. Then there are the mass extinctions. 5 major ones in the last 500 million years. The Permian extinction killed 90% of all species. The Cretaceous extinction, caused by an asteroid impact, ended the dinosaurs. Each extinction was a catastrophe, but also an opportunity. New niches opened up. Survivors diversified to fill them. Mammals remained small and insignificant for over 100 million years while dinosaurs dominated. The asteroid that struck 66 million years ago cleared the way for mammals to expand, eventually leading to primates and us. What if that asteroid had missed? Would dinosaurs still rule? Would intelligent reptiles have evolved instead? Or would something else entirely have happened? We can't know, but it's clear that our existence depended on that impact. Remove it from history and we probably don't exist. The path changes completely. Even within primate evolution, the story is full of contingency. Our ancestors came down from trees, started walking upright, began using tools. Why? Maybe climate change reduced forests, forcing adaptation to savanna environments. Maybe upright walking was more efficient for travel. Maybe it freed hands for carrying food or offspring. Whatever the reasons, it happened in our lineage but not in others. Chimpanzees, bonobos, gorillas, they all remained quadrupedal. We took a different path. Tool use led to bigger brains. Bigger brains required more energy, which meant better food sources, which might have come from cooking. Fire changed everything, making nutrients more accessible, reducing the need for large digestive systems, freeing up energy for even larger brains. But controlling fire isn't easy. It might have taken hundreds of thousands of years to master, and it required the right environment, places where lightning strikes start fires that early humans could capture and maintain. Language emerged somewhere in this process. We don't know exactly when or how. It might have started as simple vocalizations and gradually become more complex. Or it might have appeared relatively quickly once the right neural structures evolved. Either way, language transformed us. It allowed knowledge to accumulate. Each generation could teach the next, building on previous discoveries instead of starting over. Culture became possible, the transmission of information outside genetics. All of these steps, the moon-forming impact, the mitochondrial merger, the move to land, the mass extinctions, the specific environmental pressures in Africa that shaped primate evolution, the development of language and fire, were contingent. They didn't have to happen. They happened here, in this sequence, producing this result. But rewind the tape and play it again, even on Earth, and you'd likely get something different. Now multiply that uncertainty across the universe. Every planet has its own history, its own sequence of events. Maybe most never get the right collision to form a stabilizing moon. Maybe the mitochondrial merger is incredibly rare, a fluke that almost never repeats. Maybe mass extinctions usually wipe out too much, preventing recovery. Maybe the environmental conditions that pushed our ancestors toward intelligence are unusual. Maybe fire is harder to discover on most worlds. If our path is highly specific, then intelligence like ours might be vanishingly rare. Not because it's impossible, but because it requires so many things to go right in exactly the right order. You need the right planet, the right moon, the right history of bombardment and volcanism, the right climate swings, the right extinctions at the right times, the right ancestors in the right environments making the right adaptations. Miss any one step, and the whole trajectory changes. This doesn't mean life is rare. Life might be common, but intelligent. Technological life might require a story so specific that it's told only once in a galaxy, or less. We might be the product of a sequence so improbable that trying to replicate it is like trying to shuffle a deck of cards and get them in perfect order. Possible in principle, but so unlikely you could shuffle for the age of the universe and never see it happen. If true, we're not just alone, we're unrepeatable. We search for life like ours. We look for planets in habitable zones, places where water can exist as a liquid. We scan for oxygen in atmospheres, a gas that on Earth is produced by photosynthesis. We listen for radio signals, the kind we ourselves broadcast. We imagine civilizations building cities, using technology, sending messages into space. In all of this, we're making an assumption. We're assuming that life elsewhere would be recognizable, that it would follow patterns we understand, that intelligence would look something like us. But what if we're wrong? What if life takes forms we haven't imagined? What if intelligence develops along paths that don't include radio telescopes or cities or anything we'd recognize as technology? We might be surrounded by life, by minds, by civilizations, and simply not see them because we're looking for the wrong things in the wrong ways. Consider how limited our perspective is. We know one example of life, Earth, one data point. From that single example, we've extrapolated what life needs: water, carbon-based chemistry, certain temperature ranges, energy sources. These requirements make sense based on what we know, but they're based on a sample size of one. It's like meeting one human and assuming all intelligent beings must be bipedal, oxygen-breathing, carbon-based organisms between 5 and 6 feet tall. The generalization might be completely wrong. Life on Earth uses DNA, but maybe elsewhere it uses something different. A different coding system, different molecules, different mechanisms for reproduction and evolution. We wouldn't recognize it as life if we saw it. We'd think it was just complex chemistry, interesting patterns in rock or liquid, but not alive. Our tests for life are designed to find Earth-like life. Anything too different slips through undetected. Intelligence could be even more varied. We think of intelligence as problem-solving, tool use, communication, the things humans and a few other Earth animals do. But those might just be our versions. Intelligence on a water world might never develop hands or tools. It might be entirely social, entirely mental, intelligence without artifacts. We'd look at that planet and see animals swimming around, and we'd conclude there's life but no civilization, no technology, no one to talk to. But we'd be wrong. They might be having complex thoughts, creating art through bioluminescence, building societies with hierarchies and culture, just not in ways that leave physical traces we recognize. Or consider life that operates on different timescales. Trees on Earth live for centuries but don't seem intelligent to us because they operate slowly. But what if there's life that thinks on timescales of thousands of years, each thought taking decades, conversations spanning millennia? To them, we'd be too fast to perceive, our entire civilization flashing by like a lightning strike. To us, they'd seem inert, just part of the landscape. We'd never recognize each other as minds despite potentially occupying the same space. The opposite is possible too. Life that thinks much faster than us, operating in nanoseconds instead of seconds. To them, we'd be frozen, statues barely moving. They could observe us the way we observe geological processes, noting tiny changes over what they perceive as vast stretches of time. They might communicate, might have civilizations, but in burst transmissions lasting microseconds. We'd never catch them. Our instruments aren't designed for that time scale. Then there's the question of substrates. We're carbon-based, but silicon could potentially support complex chemistry under different conditions. Life in the clouds of gas giants might be based on entirely different elements. Plasma-based life in the atmosphere of stars isn't impossible in principle, though it seems unlikely. We don't know the limits. We only know what works here, and here might be just one option among many. Intelligence might not even require biological substrates. We've already discussed post-biological civilizations, but what if some life starts non-biological? What if intelligence can emerge directly in crystals, in electromagnetic fields, in quantum states? We assume life must begin with chemistry, reproduction, evolution. But maybe there are other paths to complexity and awareness, paths that wouldn't leave biosignatures, wouldn't need planets, wouldn't communicate in ways we'd recognize. Our search methods are tuned for ourselves. SETI listens for radio signals because we use radio signals. We look for industrial pollution in exoplanet atmospheres because we produce industrial pollution. We search for megastructures because we might someday build megastructures. But an alien civilization might never go through a radio phase, might never pollute their atmosphere, might never feel the need to build Dyson spheres or space habitats. Their technological path could be completely different, based on principles we haven't discovered, using resources we don't recognize as resources. Even communication assumes similarity. We send mathematical patterns into space, prime numbers and geometric diagrams, because we think math is universal. And maybe it is. But that doesn't mean everyone expresses it the same way, or considers it worth transmitting. A civilization might use quantum entanglement for communication, leaving no electromagnetic signature at all, or they might communicate through gravitational waves, or something more exotic. We wouldn't hear them because we're not listening on those channels. There's also the possibility that intelligence manifests in collective rather than individual forms. We think of minds as residing in individuals, single brains processing information. But what if intelligence is distributed? What if a whole ecosystem functions as a single mind, with individual organisms as cells? We'd look at it and see a forest or an ocean, not realizing the whole thing is thinking, processing, aware. We wouldn't know how to talk to it even if we could recognize it. Our hubris lies in expecting the universe to conform to our experience. We're pattern matching, looking for ourselves in the stars, and maybe that's inevitable. We can only search for what we can imagine, and our imagination is limited by what we know. But it means we might be missing things. We might be looking directly at evidence of life or intelligence and not seeing it, because it doesn't fit our expectations. This doesn't solve the Fermi Paradox. If anything, it deepens it. If life and intelligence can take countless forms, many of them undetectable by our methods, then the universe might be crowded. But we'd still be functionally alone, unable to recognize our neighbors, each form of intelligence isolated in its own perceptual bubble. The silence wouldn't mean absence. It would mean incompatibility, a failure of recognition rather than a failure of life to arise. And that might be the most humbling possibility of all. Not that we're alone, but that we lack the perspective to see who else is here. Imagine you wake up in a vast empty house, room after room, floor after floor, and you're the only one there. You call out and hear only echoes. You search and find no one. Eventually you must accept the possibility that this enormous place, with all its space and potential, belongs to you alone. Not because you claimed it, but because there's no one else to claim it. What do you do with that responsibility? This is where we might find ourselves. If we truly are alone, if we're the only intelligent technological civilization in the universe, or at least in our galaxy, then everything ahead of us is ours to shape. The future of consciousness, of thought, of meaning itself rests on our choices. There's no one to learn from, no one to guide us, no one to save us if we fail, and there's no one else to carry forward the project of understanding the cosmos if we don't. The responsibility is staggering. Every planet we might someday reach is lifeless until we bring life to it. Every star system is dark, in the sense of being unobserved, until we arrive to witness it. The universe has spent billions of years building toward complexity, toward galaxies and stars and planets and chemistry and somehow, improbably, us. And if we're the only ones who made it this far, then we're the universe's only chance to know itself. That sounds grandiose, maybe even arrogant. But consider what consciousness does. It takes the universe, which simply exists without comment or reflection, and creates meaning from it. A sunset is just photons scattering through atmosphere until someone watches and feels something. A mountain is just rock uplifted by tectonic forces until someone sees it and calls it beautiful. The universe doesn't care about itself. It doesn't care about anything. But we care. And if we're alone in caring, then our caring is what gives the universe whatever meaning it has. This isn't about humans being special or superior, it's about the responsibility that comes with being a witness. If you're the only person who sees something, you become its keeper, not its owner, but its guardian. You carry the memory of it, you preserve the knowledge of it, and if no one else is out there doing this work, then we must do it alone. But responsibility cuts both ways. If we're the first, we're also the most vulnerable. There's no established galactic community to help if we stumble. No older civilizations to share their solutions to the problems we face. No backup, no safety net, no guarantee that intelligence will persist. If we destroy ourselves through war or environmental collapse or technologies we can't control, then we don't just end humanity. We might end the universe's only conversation with itself. That should change how we think about existential risks. Nuclear weapons, climate change, artificial intelligence, biotechnology, all the ways we might fail. These aren't just human problems, they're cosmic problems. If we're alone, our survival matters not just to us, but to the universe's capacity to be known. Every time we come close to catastrophe and pull back, we're not just saving ourselves, we're preserving something irreplaceable, the only instance of reflective consciousness that might exist. This responsibility extends to how we treat our world. Earth is the cradle of the only known life in the universe. Every species here represents billions of years of evolutionary experimentation, unique solutions to survival that exist nowhere else. When we drive species to extinction, we're not just losing something on Earth, we're erasing possibilities from the cosmos. If we're the only planet with life, then biodiversity here isn't just local value, it's universal value, the only value there is. And if we eventually reach other worlds, if we spread beyond Earth, the responsibility grows. Every planet we terraform, every moon we colonize, every asteroid we mine, we're making choices that will shape the future for millions or billions of years. There's no one to check our work, no council of galactic elders to approve our plans. We decide, and those decisions matter infinitely because they're the only decisions being made. Some find this prospect lonely. The weight of being first, of carrying the future alone, feels crushing. But there's another way to see it. If we're first, we set the template. We decide what spacefaring civilization looks like. We establish the ethics, the principles, the values that guide expansion into the cosmos. We're not constrained by existing structures or expectations. We can choose who we want to be, what we want to become, without reference to anyone else. This is freedom as much as responsibility. If the galaxy is empty, we can fill it with whatever we think is worth preserving. Cooperation instead of competition, diversity instead of uniformity, curiosity instead of conquest. We write the story because there's no other author. That's terrifying, yes, but also magnificent. We're not latecomers adapting to an established order. We're pioneers creating something new. There's also the question of what we owe to potential future civilizations. If we're first, we might not be last. Intelligence might arise elsewhere given enough time. What kind of galaxy do we leave for them? Do we spread so widely that we claim everything, leaving no room for others? Or do we expand carefully, preserving places where other life might someday emerge? Do we leave signs, messages, warnings about the mistakes we made? Or do we let them find their own way? these aren't immediate concerns. We're nowhere near colonizing even our own solar system, let alone the galaxy. But thinking long-term is part of the responsibility. If we're playing a game where we're the only player, we need to think many moves ahead. The decisions we make in the next few centuries could constrain or enable possibilities for millions of years. Being first also means we decide whether the universe remains silent or begins to sing. We could choose to broadcast, to send messages that future civilizations might someday hear, even if they arrive long after we're gone. We could build monuments, information preserved in durable forms, so that anyone who comes later knows they're not the first to wonder, to search, to feel alone. We could be good ancestors to beings we'll never meet, species that don't yet exist but might someday. Or we could stay quiet, stay small, choose not to spread. That's also a choice, and maybe a valid one. Maybe the universe is better left mostly empty, untouched, wild. Maybe the responsibility of being first is to act with restraint, to recognize that our existence is improbable and precious, and shouldn't be imposed on everything we can reach. We don't know yet which path we'll take. We're still figuring out how to survive the next century, let alone the next million years. But if we are alone, these questions will eventually demand answers, and whatever we choose will matter more than anything has ever mattered before, because there's no one else to choose differently. There's a strange thing that happens when you sit with the possibility of being alone for long enough. The fear begins to shift, not disappear, but transform into something else, something quieter, maybe even peaceful. Because if we're alone, truly alone, then the universe becomes ours to understand without competition or threat. The silence isn't hostile, it's just silence. And in silence, there's space to think. Consider what it means to be the only ones asking questions. Every mystery we encounter, from the smallest quantum phenomena to the largest cosmic structures, is ours to explore. No one else is racing to the answer. No one else has already figured it out and moved on. The universe is an unsolved puzzle, and we're the only ones working on it. There's something beautiful in that. Pure discovery, undertaken not for advantage or survival, but simply because we want to know. If other civilizations existed, especially older, more advanced ones, we'd always be in their shadow. They'd have solved problems we're still working on, discovered things we're still searching for. We'd be children in a universe of adults, following paths already walked, learning lessons already learned. But if we're alone, we're pioneers. Everything we discover is being discovered for the first time. Every question we answer creates new knowledge that has never existed before. We're not catching up. We're leading, because there's no one ahead of us. This changes the meaning of our struggles. When we face problems, climate change, resource scarcity, social conflict, it's easy to feel overwhelmed. But if we're alone, these aren't just human problems, they're universal problems. The first and possibly only test of whether intelligence can organize itself wisely. Every solution we find, every challenge we overcome, is a proof that intelligence can work, that consciousness can survive its own power. And if we succeed, we'll have done something unprecedented in the history of the universe. We'll have made it through. There's also freedom in solitude. No one is watching. No one is judging. We can make mistakes without an audience. We can try things, fail, learn, adapt, all on our own timeline. If we're part of a galactic community, we'd face expectations, comparisons, pressures to conform to established norms. But alone, we define our own norms. We decide what civilization means, what technology should pursue, what values matter. We're not imitating anyone. We're creating something genuinely new. And consider the alternative. If the galaxy were crowded, we'd face competition for resources, territory, influence. We might encounter civilizations hostile to our existence or indifferent to our survival. The dark forest scenario, while pessimistic, captures a real possibility. Other intelligences might be threats. But if we're alone, there are no threats except ourselves. No alien invasions, no existential competition, no need to hide or defend. We can expand at our own pace, in our own direction, without fear of encountering something more powerful than us. Loneliness often comes from wanting connection and not finding it. But there's another kind of solitude, chosen or accepted, where you stop seeking what isn't there and start appreciating what is. If we're alone, we still have each other. 8 billion humans, countless other species, all of us sharing this planet, this moment, this cosmic story. Maybe that's enough. Maybe the connections we build here, among ourselves, matter more than hypothetical connections to distant strangers we'll never meet. There's also the question of meaning. We often assume meaning comes from outside, from recognition or validation by others. But meaning can be internal. The universe doesn't need to acknowledge us for our lives to matter. We acknowledge each other. We create meaning through our relationships, our work, our art, our understanding. If we're alone, that meaning doesn't diminish. If anything, it becomes more precious, more important to preserve, because it's all there is. Some of the most profound human experiences happen in solitude. Contemplation, meditation, the quiet moment when you understand something for the first time. Being alone allows depth. It removes distraction. It forces you to confront reality directly without intermediaries. Maybe that's what we're doing as a species, confronting the universe alone, without guide or companion, learning to see it clearly on our own terms. There's comfort in knowing we're not competing for cosmic significance. We don't have to prove we're the best or the brightest. We don't have to measure up to anyone else's achievements. We simply exist, doing what we do, exploring and learning and trying to survive. That's enough. That's everything. Because if we're alone, there's nothing to be better than. We're the universe's intelligence, singular and sufficient. And perhaps the deepest comfort is this. If we're alone, then every act of kindness, every moment of beauty, every thought that reaches toward understanding, happens for the first time in cosmic history. When you help someone, that compassion isn't common. It's rare, maybe unique. When you create something beautiful, music or art or even a well-lived life, that beauty is unprecedented. The universe has never seen it before. You're not adding to a vast collection, you're starting one. This doesn't erase the sadness of solitude. The longing for connection with something beyond ourselves is real and deep. But it suggests that being alone isn't the worst outcome. It's not emptiness. It's responsibility, yes, but also opportunity, freedom, a chance to define ourselves without constraint. And if we eventually discover we're not alone, if someday we hear that signal or meet those minds, we'll approach them not as suppliants seeking approval, but as equals, fellow travelers. Because we'll have made our own way through the darkness and learned to be at peace with it. The comfort of solitude is accepting that the universe owes us nothing. No companions, no answers, no safety, and then realizing we can create these things ourselves. We can be each other's companions. We can find our own answers. We can build our own safety, not because anyone told us to or showed us how, but because we decided it mattered. And that decision, made freely in the face of cosmic loneliness, might be the most meaningful thing consciousness has ever done. We're still listening. Right now, as you rest, as your thoughts drift and settle, radio telescopes are pointed at the sky. Arrays of receivers scattered across the planet, synchronized and patient, scanning frequencies for patterns that couldn't be natural. The SETI program continues decade after decade, finding nothing but refusing to stop, because the absence of a signal today doesn't mean there won't be one tomorrow, or next year, or in a century. This is the long watch, humanity standing vigil at the edge of the known, looking outward, waiting, not passively but actively. We build better instruments, we develop new methods, we expand our search to cover more stars, more frequencies, more possibilities. We send our own messages, carefully crafted attempts at communication, launching them into the void with hope but no expectation. And we keep searching for life in any form, sending rovers to Mars, planning missions to the icy moons of Jupiter and Saturn, wondering if even microbes would answer the question of whether we're alone. The watch isn't just about finding others, it's about not giving up on the possibility. It's about maintaining the question, keeping it alive across generations. Children today grow up learning that we're searching, that we don't know yet, that maybe someday we'll find something. They inherit the watch from us, as we inherited it from previous generations. The search becomes part of what we are, part of how we understand our place in the cosmos. There's something noble in this persistence. We've been listening for decades without success. Most scientific experiments that produce no results after so long would be abandoned. Resources would shift elsewhere. But this search continues because the stakes are so high. Finding even one other civilization would transform everything. It would answer the oldest question we have. So we keep looking, knowing the odds are long but unwilling to accept that silence is final. And maybe the search itself is the point. Maybe the act of looking, of reaching out, of refusing to accept isolation, defines something essential about consciousness. We wonder, we seek, we hope. These aren't just human traits. They might be universal properties of minds that can reflect on their own existence. If other intelligences exist, they're probably searching too. They're probably wondering the same things, feeling the same uncertainty, maintaining their own long watch. The question changes as we age. When SETI began, the scientists involved thought they might find an answer quickly. The galaxy seemed large, but radio was powerful, and surely someone was broadcasting. Decades passed. The silence persisted. Now the searchers are more cautious, more aware that the question might not be answered in their lifetimes. The watch has become generational, something you contribute to, knowing you might never see the result. This requires a different kind of patience. Not the patience of waiting for something imminent, but the patience of participating in something larger than yourself. You plant a tree knowing you won't sit in its shade. You build a cathedral knowing you won't see it completed. You listen to the stars knowing you might never hear an answer, but someone after you might. And that's enough reason to continue. The watch also keeps us honest. Every time we look up, every time we point our instruments outward and find nothing, we're reminded of our uncertainty. We don't know. We might never know. And living with not knowing, accepting it without despair or false certainty, requires a kind of courage. The courage to keep asking questions that might not have answers. The courage to be comfortable with mystery. In some ways, the question has already changed us. Before we started searching, we assumed things about the universe. Now we know we don't know. We've learned humility. We've learned that being the only observable intelligence is possible, even if it seems unlikely. We've learned that the universe is under no obligation to provide us with neighbours, or meaning or anything beyond the raw material of existence. And we've chosen to search anyway, not because we're guaranteed success, but because the search matters, and perhaps it's worth considering that the search might never end. Not because we'll never find anything, but because even if we do, new questions will emerge. If we find microbes on Mars, we'll ask if complex life exists elsewhere. If we find complex life, we'll ask about intelligence. If we find intelligence, we'll ask if we can communicate. If we can understand each other, if we're compatible. The questions never stop. They just evolve. This isn't frustrating. It's what minds do. We push at the boundaries of knowledge, and when we expand them, we discover new boundaries. The horizon moves, but it's always there, always calling us forward. The long watch is really a commitment to this process, to always looking beyond what we currently know, to never settling for the limits of our present understanding. Somewhere in all of this there's peace, not the peace of having answers, but the peace of being okay without them, the peace of knowing you're part of something ongoing, something that connects past and future through the present moment. The astronomers who first wondered if other worlds existed couldn't have imagined the telescopes we use now. And we can't imagine what tools future generations will develop, but we're all part of the same project, the same long conversation between humanity and the cosmos. And you, listening now, wherever you are, you're part of it too. Just by wondering, by considering the possibility that we might be alone or might not be, you're participating in the watch. You're carrying the question forward. You're one more mind in a chain of minds reaching back to the first human who looked up at the stars and asked if anything looked back. The watch continues. The silence continues. And we continue, patient and wondering, keeping vigil in the darkness, waiting for the universe to speak, or learning to be content if it never does. Because the watching itself, the attention we pay to the mystery, might be enough, might be everything. The universe became conscious through us, and conscious things watch, wonder, and wait. That's what we do. That's what we are, and we'll keep doing it, keep being it, for as long as we're here to wonder.